Okay, this is David Zierler, Director of the Caltech Heritage Project. It's Thursday, February 3rd, 2022. I'm delighted to be here with Professor Martin Israel. Marty, it's great to be with you. Thank you for joining me today.
I'm happy to be with you.
Marty, to start, would you please tell me your title and institutional affiliation?
Well, right now I am Professor Emeritus at Washington University in St. Louis.
Marty, when did you go emeritus?
Technically, I just went emeritus this last July 1. I've been only emeritus for less than a year. In fact, my last non-emeritus year was a transition year in which I was not doing any classroom teaching, which the timing of that was set a number of years earlier, turned out to be just fine because I only had half of my last teaching semester under COVID.
Marty, just as a snapshot in time, what are you working on these days?
I am supposedly retired. In fact, I'm working very closely on a project, one of several projects that I was working on when I retired, and I'm still working on data analysis and preparing a paper with my colleagues on the CRIS experiment on the ACE spacecraft, which has a definite Caltech connection. The PI is Ed Stone, and in fact, just yesterday at noon, or well, 12:30 my time, I was on the weekly ACE CRIS conference call, or conference Zoom, in which we were discussing the analysis work, which right now is mainly being done by me with my colleague, also retired here at Washington University, Bob Binns, and Mark Wiedenbeck, who is technically at JPL, but in fact is part of the cosmic ray group at Caltech. We've been working very closely with Mark, Bob, and I, and a total of a dozen people involved in this paper. So basically, the CRIS experiment was designed to measure isotope composition of cosmic rays up to nickel. Nickel element number 28 was the heaviest that was planned, because CRIS was only guaranteed a 2-year lifetime with 5 years as a goal. And in that time, the area that I've been most involved with, which is the very rare elements heavier than nickel, with the atomic number greater than 30, at that time there was no hope of getting any statistics for those particles in the lifetime of ACE. But ACE was launched, as you probably know, in the fall of 1997, and ACE and CRIS is cosmic ray isotope spectrometer. CRIS is one of the instruments on ACE, and it is still operating today. And so the paper that I'm working on with my CRIS colleagues right now is on the isotope composition of the elements of charge 29, 30, and so on up to 38, where using 20 years of data, a little more than 20 years of data, we're able to get adequate statistics to say something useful that wasn't in the plan. So anyhow, that's the main thing I'm working on now, aside from all sorts of things around the house that I've been putting off, and now are things I can be doing because I'm, retired.
Marty, more broadly, what have been some of the main areas of research over the course of your entire career?
Well, the main area has been cosmic rays, and primarily these rare heavy cosmic rays. Shortly, when I first came here in 1978, I guess, I was working with my then colleague, Joe Klarman, and with Bob Binns, who was actually working with us, even though he was in the research arm of McDonnell Douglas Aircraft. And we've been working on the composition of these rare elements heavier than charge 30. Now, until the ACE-CRIS experiment, all of the work involved the element composition. We had very large area instruments with 10 square meters or so on high altitude balloons or on the HEAO-3 spacecraft, measuring the composition of these heavy elements. So my main focus has been the composition of the rare, what are called ultra heavy cosmic rays, and all the way up to the actinides like uranium, for which we have very, very few, even with enormous detectors. The point is, element composition in the cosmic rays, like in the solar system, drops precipitously as you go up in atomic number. And so it's a challenge measuring these heaviest. But that's most of my research career. I had a 10-year intermission in the research career when in 1987, the Dean of Arts and Sciences here in March of 87 was rather abruptly shown the door by our chancellor. And a week later, of course, everyone was wondering who would replace him. And a week later, I got a phone call from our chancellor, William Danforth, MD, longtime chancellor at Washington U. Marty, I had worked with him on some other projects. Marty, Max and I are sitting here trying to decide what to do. Max Cowan at the time was provost. And I wonder if you would come over and talk with us. And then after a pause, Bill said, Marty, you might want to have your guard up. And 2 days later, I was the acting Dean of Arts and Sciences. And for the next 7 years, I was the Dean of Arts and Sciences, which is a very exciting business. Arts and Sciences here is all the sciences that I knew something about, plus the social sciences, the humanities, a department of music, a department of education, a department of performing arts. And then after 7 years of that, I was 3 years in the central administration as one of several vice chancellors. And so during that time, I was mainly interested sideline observer of the research work of the Cosmic Ray Group, which continued with my colleagues here at Washington University. And they were gracious enough to welcome me back into the group when I left. I sometimes jokingly say escaped administration. So it was a very interesting 10 years, but totally divorced from my research program.
Marty, I wonder if you've ever reflected on how your work in cosmic rays carries on the legacy, really starting with Millikan and the birth of modern physics at Caltech.
Well, it does in many ways. It carries on a. By the way, I keep getting. Are you hearing me? Okay, I keep getting a little notice that says my internet connection is weak.
No, we're fine. I can hear you.
Okay. If I drop out completely, I don't know if you have my cell phone number, but I could tell you that. Well, for now, we'll leave it. If necessary, well, no, I can't call you. I don't know. My cell phone number is 314-504-6263. So if necessary, that's a backup.
Okay, I got it.
Okay, so so it sort of carries on the Millikan work, but it's my University of Chicago introduction to the field also has great ties to Caltech. In the summer between my third and fourth year as an undergraduate at University of Chicago, I worked in the laboratory, as an undergraduate assistant in the laboratory of John Simpson, who is one of the major figures in the early days of real cosmic ray work, really understanding the composition of cosmic rays. And in working in his lab, as often happens in such things, he assigned me to work with one of his graduate students who was working on his research project. This graduate student of his is a fellow named Ed Stone. And so I worked with Ed there. I met briefly a graduate student who was working in one of the related cosmic ray labs, a graduate student named Robbie Vogt, V-O-G-T, Rochitz Vogt, whom I went on to. He was my thesis advisor when I was at Caltech. But so that kind of starts at the University of Chicago with that group. And I have been on and off, mostly on, involved in collaborative experiments involving the Caltech Cosmic Ray Group. And as I say, I was talking to Ed Stone just yesterday on our weekly noon Zoom call. So that goes way back.
Well, Marty, let's set the stage for your graduate work at Caltech. First, what years were you at the University of Chicago for an undergraduate?
It would be 58 to 62. I graduated in spring of 62, and that's when I was at University of Chicago. I grew up on the south side of Chicago, about 5 miles from the University of Chicago. I lived on campus, but often went home with friends of mine in the dorm for a home-cooked meal on a Sunday evening. But I was at the University of Chicago, as I say, 5 miles from where I grew up. And there were, I worked, as I say, in several different research groups over my undergraduate career with actually the last thing in the summer between my graduating from Chicago and starting at Caltech, I worked in a group out at Argonne National Lab analyzing bubble chamber photographs for Roger Hildebrand, who also did some important cosmic ray work subsequently in his career. So I had advice from various people about good places to go for graduate work in physics, and one was the University of Chicago. I went with a colleague of mine, a friend of mine, a classmate of mine at Chicago, to a few of those grad schools during my sort of the summer between my third and fourth year to look at possible graduate schools. I went to several places on the East Coast, Columbia, MIT, I'm not sure where else I went. I never went west of Chicago to graduate schools, but the places I went to on the East Coast, well, obviously were good places, but they just didn't click for me. And I kept hearing from people at Chicago about Caltech, and so I applied there along with several other places, and when I was admitted, I went to Caltech. One of the people I knew at Chicago who was a Caltech PhD was Eugene Parker. That's a name you may know. Caltech is involved in what is now referred to as the Parker Solar Probe.
Right. Named
after Eugene Parker for his work with the solar wind. So that was part of my influence about Chicago, but it was just kind of everyone I talked to in the physics department there for advice said, oh, Caltech is... So I went to Caltech. My first year at Caltech, of course, I was mainly taking courses. During my first year at Caltech, I was thinking I may want to be a theorist. And I worked, I don't know if it was part-time during the school year, but certainly during that first summer after my first year with Leverett Davis. Leverett Davis was a, excuse me. Leverett Davis did theoretical work on essentially interstellar and interplanetary medium. And I did some work with him, and I decided trying to be a theorist wasn't right for me. And then I looked around, and after talking with several people, I joined Robbie Vogt in his lab. At that time, Robbie was just a new assistant professor. And I was one of his first two graduate students. The other one who was there at the same time as I was Peter Wenzel, who technically is a graduate of, I forget where, in Germany, but he was doing his research work with Robbie and Ed, actually, because not long after I joined Robbie's research group, he was joined by a research associate, Ed Stone, whom he obviously knew from Chicago. And while Robbie was my official thesis advisor, in fact, Ed, as one of the senior people in that research group, was also a big help to me. And I learned a lot as a graduate student from Robbie and from Ed. So technically it was only Robbie was my thesis advisor, but in fact Ed and Robbie both played a major role in advising me through that thesis.
Marty, what was Robbie working on at that point?
Oh, cosmic rays, cosmic ray electrons. His thesis work at Chicago had been actually the first direct measurement of cosmic ray electrons. This is work he did with Peter Meyer, who was a professor at University of Chicago. So my thesis, working with Robbie, was a continuation of Robbie's work on cosmic ray electrons. We built an instrument to measure cosmic ray electrons. He was also working along with Ed Stone, developing solid state detectors for measuring silicon solid state detectors for measuring the composition of cosmic rays, mainly the light cosmic rays, protons alpha particles, that is helium nuclei, and so on. So he was working on both of those, and I, well, as I say, I, as a graduate student, was working on the electron project. We built an instrument to sort of carry the next step from his thesis electron work. And Peter was mainly working with the solid state detectors on the proton alpha detection.
Marty, what were some of the big theories in cosmic ray physics at that point?
Well, the big issues had to do with understanding. Well, there were a lot of things. I mean, ultimately, the question was, where do they come from? Where are they accelerated? It was already pretty well understood that they got their they must have gotten their energy from supernova explosions, because you look at the energy in cosmic rays and look at for astrophysical phenomena that could have produced that, and there was that. The main theory, there was a book entitled, I think, Cosmic Ray Physics, which is probably, I don't know if it's on my bookshelf here or if it's still, by the way, here is my office in the basement of home. I still have a number of my books in an office, not my longtime office, but an office that I share with another retired professor. But in fact, given all the COVID nonsense, I have been mainly working in my office here. Anyhow, there was a book by Ginzburg and Siravatsky, V.L. Ginzburg, the famous Russian physicist, which kind of at the time, that was the Bible for where cosmic rays came from.
Marty, let's talk about Richard Feynman. When did you first meet him?
Well, I never, in my time at Caltech, met him. When I got to Caltech, I had an NSF fellowship. I forget what it was called, but it was an NSF competitive fellowship. But to supplement the NSF stipend, I was given a very part-time job, tape recording and photographing the Feynman Lectures. So my job was to sit in the back of the lecture hall, running the good old-fashioned reel-to-reel, you remember those tape recorders, and snapping a photograph whenever he finished filling a blackboard. And it was that was my first year at Caltech. The 62-63 academic year was the second year that he gave those lectures. The first year, the guy who gave them, I think I mentioned to you in an earlier email, Jim Hartle, who is, as you know very well, he's a retired professor at UC Santa Barbara. He's a member of the National Academy of Science. At the time, he was a student of Murray Gell-Mann at Caltech, and he had that job the year before I came to Caltech, and then I did it that year, my first year at Caltech. And then there was some carry-on further work that Feynman did, brushing up some of the earlier lectures, and I recorded those. The fun thing that I did was, well, my job was to photograph the blackboard each time he finished a blackboard, and finished covering it and stepped aside. I made a point whenever possible to photograph it when he was in a typical Feynman-esque position. And in fact, one of those photos that I took made its way into, I think it's the second volume of the Feynman Lectures. And I happen to have the first and third volume here. The second volume, I think, is still in my office on campus. So that was the fun part, was capturing him. So I never had an opportunity to talk with him. That was my job. The secretaries took the tape recording and transcribed it, and Matt Sands and Bob Layton worked with the transcription to turn the lectures into the written text that's bound in these wonderful red volumes. And the illustrations in the text were drawn, I drew a couple of them, but mainly, I don't know if Matt Sands or Bob Layton or someone else working with him were the ones who actually made the illustrations for the text using photographs that I snapped or that Jim Hartle snapped the previous year. Tom Harvey was the gentleman who was kind of the technician in charge of the lecture hall. He was the man who was responsible for, demonstration materials that the lecturer might use. He was also the one who set up the tape recorder and the camera and who developed the film. So, as I say, my role was very small. I will tell you an interesting story of when I did meet Feynman. Many years later, I was for several days at a meeting of some committee at NASA headquarters in Washington. I don't remember. I've been on various advisory committees at NASA headquarters over my career. I'll tell you something in just a minute, which will let you pinpoint when it happened. And I was in the lobby of the hotel where where NASA put most of its visitors, and I ran into Dick Feynman in the lobby. And so, of course, he didn't know me, but I introduced myself. And the main thing he said to me was, "Well, what brings you here?" He was there. This was the very famous Feynman role on the committee that was impaneled to try to understand the Challenger disaster, when the fact that the Challenger shuttle exploded, a minute or so after launch, killing the astronauts on board and so on. Anyhow, he was there to participate in that. And he asked me, what was I there? Well, I was there to participate in this NASA committee. He said, "How can you stand coming to these NASA committee meetings? I'm in a committee meeting, and these committee meetings are boring and tedious as hell. I will never go to another." So that was Feynman's view of that committee. I'm sure you've heard the story of Feynman in that committee. He had talked to people at JPL before actually going to the meeting who might be able to give him some insight into what happened. And it was pretty clear to a lot of people that the problem was the launch was on a very cold day, colder than any previous shuttle launch. And there's a key rubber O-ring that seals one part of the launch vehicle from another. And what was suspected and what Feynman argued for the committee is the weather was so cold that this rubber O-ring wasn't sealing. Take a piece of rubber that's nice and flexible normally and make it cold enough, and it's hard. It's not a sealant anymore. It's a piece of wire stuck in there that doesn't do the sealing job. And to illustrate that, Feynman brought with him a small O-ring, rubber O-ring, and he dumped it in a glass of ice water that was, available, and took it out and showed that a little pressure on it and it snapped. It wasn't an O-ring anymore when it was cold enough. And I think that was the final conclusion of the committee, with more investigation and analysis, that that's why Challenger went. So anyhow, that's when I met Feynman. I never met him. He had nothing, as I understand it, he had nothing to do with producing the written text known as the Feynman Lectures. It was his responsibility to create the lectures, to give the lectures, and from there on, the production of the written text was Bob Layton and Matt Sands. And so people like me had no excuse for meeting Feynman.
Marty, what was the idea, the initial idea about recording his lectures? In other words, was it understood how historically significant they were, and it should be captured and transcribed and ultimately published? Was that the plan from the beginning?
I don't know. I mean, if you look at I just, in fact, in the last few days, reread Feynman's introduction and what Layton and Sands wrote in one or another of the introductions to these volumes. And they were, apparently the physics faculty at Caltech had realized that teaching the standard physics text, from the standard physics text, the standard first and second year physics course, particularly for the very bright undergraduates who came to Caltech, was deadly boring, not very interesting. And they decided they wanted to I don't know that I think they were thinking of writing a new text. And apparently, according to one of the, I don't know, maybe it was Feynman's introduction to the book, there was at one point talk about, well, we'll all agree on the outline and different members of the faculty will take responsibility for a few lectures and one or two chapters, and we'll make a text out of that. And as I understand it, the decision was that that's not the way to do it. You need some integrating thought. And so when they asked Feynman to do these lectures, it was certainly with the plan in mind of recording them and turning them into a textbook. I don't know. Well, I don't know if people recognize how historically important it would be. I will tell you that the last couple rows of the lecture hall, when I was back there operating the tape recorder, the last couple rows were filled with graduate students, because all of us grad students understood very well that, wow, this is a new insight. We all learned from his freshman and sophomore physics lectures. It was quite clear to all of us that this was more insightful than any of us had had when we were undergraduate students and we were learning things. Excuse me, I'm just going to get some more water.
Sure.
I'll be back in just 1 minute.
Take your time.
Sure.
Marty, tell me about Feynman's lecture style. How did he convey all of his insights into physics?
Well, first of all, I'll say he was very animated, which is, as I say, something I tried to capture in the photographs I took. The one that appears in one of the books is only one of them, but someone at Caltech probably has all those photos, and in them you will find many examples of animated, interested, excited scientists talking about these things. So the idea was he wanted to give new ideas, and he talked about all sorts of things. He brought in, where does some talk about lightning? Where did all that electricity come from? I remember him talking, he said one time when he was riding the subway in New York, he noticed a picture of somebody. It was an advertisement, over the subway cars there's a row of advertisements. An advertisement for a company that made pasta, like spaghetti. And so when he was talking about stress and strain, he brought out and told people, and this is something I've done many times to people's amazement, he noticed that there was a picture that showed a woman holding an uncooked spaghetti, one uncooked spaghetti, and she obviously broken it, and it broke into 3 pieces. Basically, in each hand there was 1 piece, and something from the middle of it was flying off. If you haven't seen that in the book, go home and try it. Take an uncooked piece of spaghetti, grab the ends, and bend it. And I guarantee you're going to find a piece from the middle of it flying off. And so, having done that, he then went through the analysis that if you take a uniform object and strain it by bending it this way, that there will be 2 points where the strain is the greatest. It will not be uniform all around, and contrary to most people's intuition, it will not be the spot right in the middle. There will be 2 points, a little bit on either side of the middle of this piece of spaghetti, where the strain is greatest. And he did an analysis to show that. And obviously one of those 2 will be the spot that breaks, and then the piece will flip back, and there will have been enough strain in there that it'll flip back fast enough that the other spot will also break, and that piece will go off. So this was how a lecture on stress and strain could be deadly, or with lots of math and ho-hum. But he introduced it by breaking a piece of uncooked spaghetti. So that gives you a sense of Feynman's approach to, again, as he said in the introduction to the book, he knew he was dealing with really smart guys. And they were all guys, that's another story. But, he knew that the typical physics course bored such smart guys terribly. So he was going to make it interesting, which he did. He also made it interesting by introducing quantum ideas. And his approach to quantum, those of I don't know, do you have a physics background? I don't know your background.
I'm a historian of physics, actually.
Okay. Well, the standard way of teaching quantum mechanics is you kind of start with the Heisenberg equation, and you show solutions of that, and how you can solutions of that for the hydrogen atom from the Heisenberg Schrodinger equation. Heisenberg is part of it, but it's called the Schrodinger equation. Well, he realized that the real interesting part is the quantum nature. And so he started out by talking about Gerlach experiments, which are ways that you can separate particles with different magnetic polarization, up, down, or side. And there are basically three states that a particle of spin 1 can have, which is with the magnetic field, opposed to the magnetic field, or zero component along the magnetic field. Or in the simpler case of a spin 1/2 particle, it's either with or against the magnetic field. Those are two states. And how you can work with a multi-state system didn't require any Schrodinger equation, the basic concept. And he introduced that. And so he introduced these, well, sophomores by that time, to quantum mechanics by avoiding, I mean, usually quantum mechanics is taught only at a, like, second year or graduate. When I was an undergraduate at Chicago, the faculty had made quite consciously the decision to teach us undergraduates nothing about quantum mechanics. That's for graduate school. Because, you know, you need to be much more sophisticated in physics and much more sophisticated math to even begin to understand quantum mechanics. At least that was the idea when I was an undergraduate at University of Chicago. So I'm talking about late 50s, early 60s. And Feynman said, well, there's important parts of quantum mechanics that people should understand, recognizing that a lot of the students in this intro course are not students who would take any other physics course. They might have been chemistry majors, biology majors, but they all had to take the physics. And for them to leave without knowing anything about quantum mechanics was terrible. And so he figured out a way to introduce at least many of the key concepts of quantum mechanics without burying it in the math. Now, he did introduce math of various sorts, including in his lectures on quantum mechanics, but not solution for the hydrogen atom, solution of the Schrodinger equation. That's not easy. That's not easy math. And that's why the standard thing was keep that for undergraduate seniors, or better yet, graduate students. And Feynman said that's terrible.
Marty, what about particle physics? In what way did he convey some of the latest ideas about particle physics at that point?
I don't recall that in the lectures. I bet there was some, and if I look through the printed volumes, I might find some, but let's see, if it were there, it would be in volume 3, which I just happen to have here, knowing that we would be talking about these things. And I don't really, oh yeah, I mean, he did talk about bosons and fermions, and I don't think there was any. I don't think there was anything beyond passing comments to what was going on in particle physics at the time.
What do you think the significance of that is? As in these were not important concepts for freshmen and sophomores to grasp yet? Was there not much excitement happening in particle physics at that point? What's the takeaway?
Well, there certainly was excitement. It was around that time that quarks were being introduced the eightfold way and all sorts of things. But again, I think he was trying to make sure he wasn't mainly teaching. He recognized that the majority of the students in the class were students for whom this would be their only physics class. And I think he recognized that the basic concepts of quantum mechanics were important in chemistry, certainly, and for that matter, biology, biochemistry, and so on. And I think he felt that that was important beyond just physics. And it may well be that he was thinking, and I don't know, for me to guess what was going on in Feynman's mind is ridiculous humorous on my part. But my guess is that he was looking at what might be things that involve these non-physics majors as they move forward. And I don't think the basic ideas of particle physics were seen as likely to have an effect in science more broadly, where it was quite clear to him that quantum mechanics was quite essential to, obviously, to chemistry, but to other science as well. So that's my speculation about that. A very good question, and I hadn't thought about it, but it's a good question, and that's my best guess. But I wish you could still ask him that question.
Marty, on the topic of, or on the basis of capturing the imaginations of students who might not take additional physics classes, what about the ways that Feynman talked about the universe? Did he talk about astrophysics or astronomy? Was the term cosmology in use? Did he talk about cosmology at any point?
I don't recall that. He did talk about, one of the things I remember him saying, he did talk some about beauty in the work, in the sense of, he said, these equations are beautiful, he said, but on the other hand, if we were all colorblind, and someone published a paper about arcs in the sky that have interesting spectroscopic characters that appear after a rainstorm. Would anyone say, oh, those are beautiful, in the same way that when we look at a rainbow, we look at it and say, that's really beautiful. He said, if you were colorblind and all you had was spectroscopic analysis showing there's this arc of raindrops there, and you get mainly one wavelength from this edge and another wavelength a little further out and a different wavelength further out, people would say, yeah, that's interesting. Would anyone look at the paper and say, oh, that's beautiful? Not the same way as when we look at a really clear rainbow. So that was, again, another Feynman-esque thing that sticks in my mind. He also, I remember he liked to pose questions. Maybe I'm off what you already asked, but he liked to pose questions. And as I said, there were a lot of graduate students in the back of the room. And he posed a question that is now I find when I taught a course in electricity and magnetism for undergraduate juniors here at Washington U. The textbook essentially used an adaptation of this problem that he set for the students. And those of us who were grad students, and I lived my first 2 years there in a grad student dorm, Keck House, which was a brand new graduate student dorm when I moved into it. As I understand, the building is still there, but it's used for something. It's not a dormitory anymore. But the grad students went back discussing this. This was the problem of picture a disc, a plastic insulating disc. And on the disc, embedded in the disc, all around the periphery, are little metal balls which are charged. You put a net electric charge on they all have, let's say, a positive charge on all these balls. This disc is free to rotate. In the middle of the disc, there is a coil of wire attached to a battery. And now the initial conditions are this coil has current going through it, and this disc with these positively charged balls embedded in the plastic is stationary. Now suppose you cut the connection to the battery for this coil, so suddenly the electric current in the coil goes to zero. Now, what will happen, of course, that means there'll be a changing, there was a magnetic field out where these charged particles were, the charged thing embedded in the plastic were, there was a magnetic field produced by the DC current in this coil. And that magnetic field just changed dramatically. And if you look at Maxwell's equations, you'll see that the changing magnetic field will produce an electric field which will be pointed in the same sense at all, but now you have an electric field in the same sense all around this coil where there are these charged particles. Well, then obviously the charged particles will feel a force. And so the initial condition was everything was stationary. And after cutting this wire, now this plastic disc is rotating. What about conservation of angular momentum, he asked. And we all went home, and there was plenty of discussion among the graduate students to try to come up with an answer to that. And suggestions that were obviously wrong, like, well, there was angular momentum. All the electrons in this wire that were carrying the current were going around, and now they've all stopped. And that angular momentum was transferred. No, that didn't work. You could show that it didn't matter whether the charge carriers were negative going this way or positive going that way. The disk would end up rotating in the same sense either way. So that idea can't be right. And I don't remember what all the other harebrained ideas were. Of course, the answer, which he gave, I don't know, maybe a week later, is that E cross B has momentum. There is momentum associated with perpendicular electric and magnetic fields. And so there was angular momentum in the electromagnetic field around this stationary disk when the current was going. When the current was stopped completely, and after it had stopped and there was no more magnetic field, there was no more momentum in the E cross B because there was no longer any B field, and the conservation of momentum was that the momentum of the E cross B field was the result of, was transferred to momentum, angular momentum, in fact, in this case, of this rotating disk. Well, so that's the kind of thing he did. It wasn't a homework problem in the sense of, now solve this problem, you got to figure out which equation to plug numbers into. It was nothing like that. It was the basic concept that electromagnetic fields can carry momentum. And if they're oriented in the right way, it could be angular momentum. So again, that's the kind of thing that Feynman did, which really engaged. I mean, I know the undergraduates were also engaged, at least the smarter ones were busy trying to think about it. And he hadn't talked anything about E cross B fields having momentum associated, or that electromagnetic waves carry momentum. He hadn't gotten to that point yet. These were just simple things that came from more or less electrostatics and conservation of angular momentum, one of the most basic things that had been introduced way earlier in the course.
Marty, did Feynman discuss his own work? In other words, did he convey at all of the advances that he was making in quantum electrodynamics, for example?
I don't think so. I don't recall that in these lectures. I mean, I do remember when he received a Nobel Prize, and there was a lot of discussion in the department about it, but I don't think any of that came up. I mean, the work that got the prize, I don't think any of that, I don't think anyone talked about Feynman diagrams or anything like that in that first or second year course. Maybe I missed something, since I didn't know anything about Feynman diagrams myself in my first year as a graduate student.
What about Feynman?
So I don't.
What about Feynman talking about the physics at Caltech specifically? Some of the research at Caltech that was contributing to these advances. Did he bring a sense of institutional pride to his lectures at all?
I don't remember that, but that's not to say there wasn't any of it going on that went on and went over my head, or that something like 60 years ago. And
sure.
you'll forgive me if my memory is not completely clear.
Marty, what about Feynman's sense of history? Did he talk about the way physics research had advanced in historical context at all? In other words, did he convey how important Paul Dirac was, for example?
I don't recall any of that. I don't recall any. I'd be surprised if there weren't, at least in passing, some comments made about the history of it, but I don't recall that. That's not.
Let's move on to the mechanics.
That's a good question.
Let's move on to the mechanics. So you do the audio recording, and then what do you do with it at that point? You bring it to the secretary?
I just turn off the tape recorder and go on to my classes. And this Tom Harvey, who was the guy who set up the tape recorder, took the tape, and I assume that he was responsible for giving it to the secretary or to someone else who gave it to the secretary. And similarly, the camera, of course, those were days when photographs were taken on film, not with pulling out my handy little cell phone. And similarly, Tom took the camera, took that film, and for all I know, Tom Harvey was the one who actually developed the film and made the prints, which were then passed to Leighton and Sands, and they used those in connection with the transcript to decide what sketch belonged in the printed material. The printed material initially came out basically in loose bound pages of mimeograph. The idea was to get the printed material in the hands of these students as quickly as possible. And so the red bound volumes that you're probably familiar with, that was the second step. The first step was the transcripts, edited heavily, I understand, by Leighton and Sands. The transcripts were edited and turned into mimeograph pages that were then clipped together with, temporary kind of clippings. And those were distributed, so the students in the class got those. I don't remember exactly how quickly, but certainly within a week, they had the written text and complete with at least preliminary sketches. And I'm not quite sure how long it took to get that into the bound book. Now, let's see. The volume 1 book is copyright 1963, and the lectures that appear in volume 1 were, for the most part, in that first year before I came, which was the academic year 61-62. But the bound red Feynman lecture book, volume 1, is copyright 63. I have volume 3 here. That was copyright 65. So the bound books took a year and a half or 2 years to come out. But the students in the course had, I think it was on a time scale like a week or a few weeks, had the material in the mimeograph form.
Now, was your sense at the time that Sands and Layton intended for this to become a bound series of volumes?
Oh, yeah, I think so. I think so. The idea was, I mean, it was quite clear that they thought this would be a new physics textbook that would be widely used. What emerged was, I think within a couple years, that it wasn't a good textbook. It was wonderful material for understanding electromagnetism, for understanding quantum physics, all sorts of basic concepts. And some of the material in there, as I said, was subsequently used by other textbook writers. For a while, I was teaching the freshman physics class here at Washington U, one of the sections, the freshman physics, which was first year science, first year physics, chemistry majors, and first year engineers, and also second or third year pre-meds, of which we have a lot here at Washington U. And that was basically taught in 5 or 6 separate sections. And I taught one of those sections. And for several years, we used a new text, which I like, and many of the students did not like, which I have here. Six Ideas That Shaped Physics, written by Tom Moore, who's at Pomona, I think. Isn't that where he is? Well, I'm pretty sure Tom Moore is at Pomona, and he's created these 6 ideas that shape physics. And for example, in these texts, he introduces quantum mechanics. In Unit Q, he introduces quantum mechanics, and he introduces, in using exactly Feynman's things with Gerlach experiment and the basic ideas of specific energy states and how you convert from one to another and so on. So I'm sorry to say that most of the physics books that are used these days do not take advantage of Feynman's introduction to quantum mechanics the way that Tom Moore did. And in a sense, I like Tom Moore's book just as I like the Feynman Lectures and find it interesting and useful for my understanding. Most of the students did not think it was a good textbook in somewhat the same way that after a couple of years at Caltech, they did not, I don't know exactly when they stopped trying to use the Feynman Lectures as the text for the introductory physics classes.
Marty, this would be totally anecdotal, but do you have a sense if students came into these lectures not intending to pursue additional courses in physics, but who ended up doing just that as a result of the way Feynman conveyed these ideas?
I would bet that the answer is yes. don't. I didn't have much contact with the undergraduates. Obviously, during the lecture, I was just sitting in the back, and they were, and so some of the, they had, in addition to the lectures, the course involved recitation sections of, like, I don't know, a dozen or so students per section. And many of those recitation sections were not by graduate students, but by faculty. I know Robbie Vogt taught at least one recitation section. So those people, I'm sure, had more contact with the students than I did, and would probably be able to give you firsthand. Now, a lot of those students aren't around, but I'll tell you, Robbie is very much around. Even though he's well in his 90s, I am still in email contact with him.
Yes.
And he is, I would assume you've been in contact with him too.
Absolutely.
His mind is perfectly fine as far as I can tell.
Yeah.
And his memory of things is perfectly fine. And, that's a question that I bet he would be able to answer.
Yeah.
Firsthand, in the sense that I know he had contact with some of the students who were taking that class.
Marty, for the last part of our talk, a few reflective questions given how you were present at the creation. So for you personally, as you emphasized, you were a graduate student, but there was still much to learn from these lectures, even though they were designed for first and second year undergraduates. In what ways was being in Feynman's presence, being there for these lectures, how do you think that influenced your subsequent career in physics?
I would have trouble saying that it influenced my research career. My research career was since my research, as I said, was in astrophysics, and that really didn't come up in these lectures. But it certainly has affected my role as a teacher. I mean, after all, I'm a professor at a major university, and as such, part of my job, so to speak, is doing research, and part of my job is teaching. And I have, over my career, I have taught courses, everything from, like I say, the freshman physics class for science majors, and I've taught some physics classes for non-science, mainly astronomy, for distribution courses that's taken by history majors and other non-science majors. And I've taught courses aimed at advanced undergraduate physics majors and some graduate physics courses. So teaching has been part of my work, and certainly, as I've indicated, some of what he talked about there comes up in my classes, and I use it some, but it's not in a conscious way. I didn't say to myself, well, let me see if I can teach this the way Feynman taught it. It wasn't a conscious effort to, in any sense, emulate him, but it was more just his way of describing things helped me understand things in a way that I could explain them better. So it was more an indirect thing that it helped my teaching. I can't say it had any effect on my research career.
What do you see with the Feynman Lectures as exactly what his unique gift was? In other words, he's advancing the field in tremendously important ways but he's also conveying the ideas in a way that's accessible, even elegant. In seeing this in person, how did he do it?
Well, as I've indicated, he did it partly by his enthusiasm. I mean, that's just, it's infectious. So that's part of it. Part of it was tying it to simple puzzles that made people think, like this question about conservation of angular momentum when the electric current in this coil is disconnected, and bringing in things like breaking uncooked spaghetti. So it was, I mean, that it was mainly just his approach to making things exciting and interesting and new. Excuse me.
Well, Marty, this has been wonderful spending this time with you. I'm so glad we were able to do this and capture your connection to the Feynman Lectures. So I'd like to thank you so much.
Well, you're very welcome.